Module 5 covers Human-Machine Interface, or HMI. Upon completion of this module, students will be able to describe the basic objectives of an HMI, describe the various components of an HMI, describe the 3 mid-level principles in interface design, describe the 8 golden rules for interface design, describe the practical guidelines in interface design, describe interface design guidelines applicable to each HMI component, create an HMI using the Advanced HMI API library, and implement an HMI that communicates with a virtual PLC. First, let us investigate HMI objectives and components. A human-machine interface, HMI, provides an intuitive interface to facilitate the interaction between the human operator and the control devices. Furthermore, it enables effective process automation and monitoring by depicting process data and status using graphical displays. A sample HMI is depicted in the figure. Merriman and Adams describe an effective HMI as a result of applying human factor design criteria and methodologies. Furthermore, they specify the following HMI objectives, which are categorized and based on human factor engineering. Number 1, operational factor. Within this factor are the following: minimize errors, enhance safety, and increase system efficiency. The operational factor is focused on the efficiency and safety of operations. By facilitating the automation and monitoring of processes through an HMI, errors can be reduced and safety standards can be applied. Number 2, reliability, maintainability, and availability, RMA factor. Within this factor are the following: increase reliability, improve maintainability, reduce personnel and skill requirements, reduce training requirements. The reliability, maintainability, and availability RMA factor of the HMI objectives is centered on creating an interface that can provide increased reliability of the processes and improve the maintainability of the system. Further, by providing an effective HMI, the need for additional personnel and training can be minimized because complex operations and equipment are depicted as simple abstractions to the human operator. Number 3, human factor. Within this factor are the following: improve situational awareness, reduce fatigue and physical stress, increase comfort and confidence, reduce boredom and monotony, increase usability, and reduce task saturation. The human factor is focused on enabling situational awareness and increased comfort for the human operator. Enabling situational awareness to the human operator could potentially provide assistance in anticipating a future event that is detrimental to the entire operation. Number 4, financial factor. Within this factor are the following: reduce production downtime, prevent asset and equipment damage, increase productivity and efficiency, increase corporate sales and reputation. The financial factor relates to the ability of HMI to bring about cost savings through increases in productivity, efficiency, sales, and corporate reputation. By enhancing automation and process monitoring with the use of an HMI, downtime and equipment failure could be reduced. In general, usability issues must be of paramount consideration. Wickens et al. List the following usability guidelines. Number 1, match system in the real world. Number 2, provide consistency and standards. Number 3, make system status visible. Number 4, give users control and freedom. Number 5, prevent, recognize, and recover from errors. Number 6, limit the need for memory. Number 7, make efficient and flexible use. Number 8, make simple and aesthetic choices. These usability guidelines will be revisited in the next lesson. An HMI is made up of components that facilitate the interaction of the human operators with hardware components for control and monitoring purposes. The following discussions briefly describe the basic HMI components. Displays. HMI displays can range from liquid crystal displays, LCD, to the more advanced organic light-emitting diodes, OLED. They can also be the traditional externally controlled type to the more sophisticated touchscreen variety. An HMI with advanced display equipment is depicted in the figure below. Input. Input devices may include a mouse, a keyboard, a trackball, a digital pen, or even voice-activated input system. These devices provide the means to enter data or to activate, deactivate controls. A traditional HMI with a collection of input devices is depicted in the figure. Output. Output devices usually consist of digital displays that may also include printers and audio devices. The audio devices are mostly integrated with safety and alarm systems. Communications. The communication components enable the transfer of information from and to controllers, sensors, actuators, and so on. This information includes process monitoring data, activation and deactivation signals, alarms, and other relevant data for processing automation. Examples of communication devices include routers, switches, network cables, serial wires, and wireless modems. Data. Process data, signals, alarms, and monitoring status are just a few of the enormous amounts of information that must be handled by the HMI and presented to the operator in the most effective way. The HMI designer must be able to judiciously decide on the following aspects with regard to data that need to be presented. 1. The pertinent data to be presented to the operator. 2. The best way to present that data. 3. The interrelationship of data items. And 4. Data triage. We will now look into HMI design principles and guidelines. HMI design can be a daunting task. Factors to be considered include, but are not limited to, reliability, safety, efficiency, usability, and quality. Guidelines, standards, and handbooks on HMI design are provided by prominent organizations such as the International Organization for Standardization, ISO, and the International Society for Automation, ISA. Guidance for interface designers assumes three different forms: high-level theories and models, mid-level principles, and specific and practical guidelines. The high-level theories and models provide a framework devoid of implementation details that can be used to put together a very high-level interface design. The mid-level principles are used to create and compare design alternatives. Finally, the specific and practical guidelines are rules of practice that are uncovered by the designers. In this lesson, we will only cover the second and third form of interface design guidance. Schneiderman provided the following three mid-level principles in interface design. Recognize diversity. This principle states that a designer should take into account that people think, learn, and solve problems in different ways, and that a design should start with an understanding of the intended users of the interface. Further, the process of getting to know the user is never ending because of the many user characteristics that continuously evolve or change. Use the 8 golden rules. This principle advocates the use of the 8 underlying principles of interface design, which are heuristically derived from experience. The 8 golden rules are the following. Number 1, strive for consistency. Consistency includes, but is not limited to, the text font, colors, interactions, menus, layout, and prompts. Number 2, enable users to use shortcuts. As users gain experience in using the system, shortcuts must be provided for them to cut back the interactions and more rapidly move within the interface. These shortcuts can be a combination of keys, option buttons, and hidden commands. Number 3, provide informative feedback. A system feedback must be provided to enable constant engagement with the user. Number 4, design dialogues to indicate completion. Sequences of actions must be designed in clusters, and an informative feedback must be presented to indicate the completion of the group. This provides the user with a sense of accomplishment. Number 5, provide prevention and error handling. The system must be designed to prevent the user from making a serious error. Whenever possible, provide error handling mechanisms so the system and the user can gracefully recover. Number 6, permit reversal of actions. Design in such a manner that actions can be undone. This will provide some confidence to the user to learn more about the system through deeper system exploration. Number 7, support internal locus of control. This principle suggests that users must be given the sense of controlling the action rather than responding to actions. It provides the users with the sense of being in control and that the system is just responding to their actions. Number 8, minimize short-term memory load. This principle requires that displays must be kept simple, window motion frequently be reduced, and training time must be allocated for recognizing mnemonics, codes, and actions. Prevent errors. This principle recognizes the fact that no matter how much testing is done on an interface or any piece of software for that matter, errors are bound to happen. Schneider suggests 3 techniques for reducing the occurrence of errors: correct matching pairs, incomplete sequences, and correct commands. Unmatched pairs are a common problem. Examples of this are unbalanced parentheses, unmatched opening delimiters, and unclosed markers. This can easily be prevented by using the special features found in most programming editors. The designer may provide a sequence of steps to complete one action. This will take care of the instance in which a user inadvertently omits one or more steps to complete an action. As an example, the designer may design an interface that includes the entry for all parameters and a single button to complete the action. If one or more of the parameters is omitted, the action cannot be completed, and an error display message is shown. The designer must prevent the user from invoking incorrect commands that may jeopardize the safety of the system. An effective preventative measure is to offer the user a choice of available commands through a menu-driven system rather than allowing the command to be typed in. Storyboard creation. This is the initial step in creating an effective HMI. A sample storyboard is depicted in the figure below. A rough sketch is made to flesh out the concepts of visual controls, the flow of the information, the operator interactions, and the general navigation between screens. The visual controls may include buttons, sliders, input and output text boxes, status indicator lights, and gauges. The flow of information from and to the controllers, actuators, and sensors is an important factor to consider for proper functionally visual controls. It is imperative that operator interactions are fleshed out at the outset. Finally, the general navigation between screens must be considered to realize an effective economy of the movements of displays. Get user input. The user or operator is the primary customer for the HMI that is being designed. It is best to get the input of the users to determine their needs and familiarities. This information and the system requirements may be implemented in an HMI prototype for testing for usability and functionality. Color and automation restraint. The use of color and automation can be both beneficial as well as detrimental to the efficacy of the HMI. Automation can be a distraction to the operator and introduce additional load to the system. Automation should be used sparingly. Similarly, The excessive use of color may shift the attention of the operator from an important condition that requires immediate attention. The general rule of thumb is to reserve bright, saturated colors for abnormal conditions. Visual aids. One of the primary objectives of an HMI is to monitor process data. By using the proper visual aids, important information about the status of the process can be easily communicated. However, appropriate visual aids must be judiciously utilized. For example, displaying a water tank with a liquid level line indicator is not as effective as a tank with a text label depicting the level in numeric percentage. Availability of important items. Make critical controls visible and consistently located in the same place at all times. For safety and security reasons, operators must have immediate access to shutdown, stop, alarm, and other emergency controls at all times. Situational awareness. In some instances, displaying additional information may enhance the situational awareness of the operator. Line charts indicating a historical trend together with the current value of a process variable may provide an indication of an upcoming process abnormality to the operator. Limit screen clicks. A good rule to keep in mind is to design screens to be at most 3 clicks away from the main screen. This prevents rousing user frustration because of the difficulty of getting back to the main screen. It may even be best to keep a home button on each screen available. Beware of pop-ups. Use pop-ups sparingly. Excessive use of these displays adds very limited advantage and can be a distraction to operators. Log date and time. Logging date and time of events and interactions must be regarded as an essential design component of an HMI. By keeping a record of events, alarms, and variables, process automation can be reviewed and improved. Furthermore, these logs provide essential information that can be used for the continuous improvement of the HMI. Authenticate. Provide an operator authentication mechanism to ensure systems security. The HMI is the gateway to the entire process automation and can also be an entry point for an impending disaster. Consistency. The look and feel of an HMI must be consistent throughout every screen to preclude any confusion and distraction to the operators. An exit button that is depicted 2 or more different ways can also create confusion to any user. Later in this module, a tutorial on creating an HMI using the Advanced HMI API library is presented. A prototype implementation of the sample HMI storyboard that is created using the Advanced HMI API library is shown in the figure. The U.S. Nuclear Regulatory Commission, NRC, evaluates the human factor engineering, HFE, aspects of human system interfaces, HSIs, found in nuclear power plants. This review is in accordance with the Standard Review Plan, which is published as an NRC document. NUREG 08000. The design specification of HFE guidelines are described briefly in the following sections. The astute reader is referred to O'Hare et al. For a comprehensive treatment of the HFE guidelines. The guidelines cover the following aspects of HSI elements. Information display that provides a guideline for visual displays, which includes display formats, display elements, icons, labels, text, color, and coding, data quality and refresh rate, and display devices, terminals, video displays, and monitors. User interaction and management provides a guideline for the modes of user-system interaction, data integrity and protection, and authentication mechanisms. Controls provides a guideline for information entry, dialogue types, information retrieval and processing, and system response. It also provides guidelines for conventional control devices such as rotary controls and push buttons. Alarm system provides guidelines for the alarm system design and implementation. It includes parameters such as conditions, set points, availability, and other alarm-related information. Safety function and monitoring system provides guidelines for the review of safety functions and monitoring parameters. Soft control system provides guidelines for the information display and user interaction in soft control systems. Computer-based procedure system provides guidelines for computer-based procedure systems, including information representation, functional capabilities, backup, and system integration. Computerized operator support system provides guidelines for operator situational awareness and decision-making process. It covers the guidelines for functional requirements on simulation facilities and user interfaces. Communication system provides guidelines for speech and computer-mediated communication between personnel in the local environment, such as those found in industrial or manufacturing settings. Workstation design provides guidelines for the design of workstations, including features such as layout, ergonomic, and integration. Workplace design provides guidelines for the general workplace design, including environmental characteristics such as temperature, illumination, humidity, and noise level. Maintainability of digital systems provides guidelines for the maintainability aspects of digital systems. Now, let's look closely at how an HMI is implemented. In this module, we demonstrate the development of an HMI for the control logic system application for a simple lamp switching system. The system requirements are as follows. A control logic system needs to be implemented as a PLC application. The system requires a switch to be turned on at least 3 times to energize a lamp. The ladder logic implementation for this application is shown in the figure. When X0 is turned on and then off, the up counter is enabled and the accumulator is incremented by 1. This is repeated 2 more times, which will turn on the done bit because the preset value is reached. This will in turn energize the lamp. The application using ladder logic diagram LD is designed using the OpenPLC editor. After completing the LD program, a structured text ST program is generated that will subsequently be loaded into the simulated PLC using the OpenPLC runtime interface. The ST program is shown in the figure. For those who have programmed using the Pascal language, this should look familiar. In order to properly tie up the HMI implementation to the OpenPLC Simulated Programmable Logic Controller, PLC, the HMI designer must refer to the address mapping information shown on the tables. The step-by-step instructions on creating the ladder diagram program on the OpenPLC editor, the structured text program on the OpenPLC runtime, and the HMI development on MS Visual Studio for the counter application are found in the resource folder. The file name is titled Module5_Lab1Solution.docx. The functional HMI implementation is shown in the figure.